Hello, and welcome to this low-level JavaScript series where I'm on a quest to build, I guess, the world's first RISC-V CPU on an FPGA in TypeScript. This is episode 4 of who knows how many episodes, and it's been a while since I've actually made this video, so just also as a reminder to myself and a reminder to everyone else, what we've been doing so far is actually not building directly the CPU for the FPGA, but rather building an emulator in TypeScript for a RISC-V core. And yeah, I've talked about the reasons for that and the reasons that's a useful thing, so I won't delve into that path again. But needless to say, it's pretty useful, and it's already proving useful. And today we're going to focus on store instructions of the RISC-V instruction set. And store instructions, there are 3 store instructions. They take the form of the S-type encoding. This is the RISC-V 2.2 specification for unprivileged instruction set. So they take the S-type instruction encoding format, and it's a pretty interesting instruction. It's kind of got this 12-bit immediate value that we need to use, just like the I-type that we've already decoded. But that 12-bit immediate value is actually split up in a couple of places in the instruction. It's not just, we can't just shift it down like we did with the I-type instruction. We actually need to take these 7 bits here and concatenate them with these 5 bits down here. And together, is that correct? No, I guess I must be wrong there, because we get 12 bits out of this. But yeah, we need to basically zip these 2 bits together, and that will give us our immediate. And yeah, we'll go into all of that. So the store instructions, there are 3 of them. They're SB, SH, and SW. So SB is store byte, SW is SH is store half word, and SW is store word. So yeah, that's fairly self-explanatory. In this instruction set, a half word is a 16-bit value and a word is a 32-bit value. So yeah, that's that. Should be pretty straightforward, but we're going to need to do some scaffolding in the project and kind of get things together, and kind of in the last episodes we sort of hacked a few things together in order to get the pipeline running end to end, and also to get the idea of an ALU instruction from end to end. So one of the things we're going to be doing is kind of cleaning some of that up and making it a little bit more, getting a little bit more towards the actual architecture that we're going for here. So let's zip back over to the code, and well, this is actually my todo.md, which I haven't committed to the repository. So the follow-up business for this episode is the first follow-up. This is actually the first episode that I'm making since I made the 3 previous episodes. So this is the first one with actual follow-up. And one of the things I want to follow up on is that Ben Smith left me a comment on one of the videos, and he told me just a tip for efficiently converting int32 to uint32. And it's funny because, well, maybe there was something in that first episode, but I actually really needed and ended up going down a different route for that in the 3rd episode, well, the previous one. And this tip is great. I actually benchmarked it, and it's like more than twice as fast, and yeah, simpler as well. So that's really nice. I'm really happy to put that in. So thanks, Ben, for that, for one. Before we do anything, let's just go and do that. That's going to be in this, there's going to be all sorts of me struggling to use my keyboard in this, because I've recently moved from OS X back to Linux, and I'm just like having to reacquaint myself with the fact that command is not like the primary thing anymore. Alright, so aside from that, so we had this idea of this twos function. It's actually a really useful little function. We can take something that's going to be like maybe a negative number and just like convert it to the actual twos complement representation of that number as a 32-bit integer. It's super useful. It allows us to get at the bits the numbers in the way that we actually need to. Get things out of those like GUI, negative JavaScript numbers and get them into this nice realm of like, hey, these are all 32-bit values. I'd kind of the way I did it was I made this temporary variable, not really a temporary variable, but sort of just this like hidden variable here, which just has a one element uint32 array. And basically, in order to convert stuff, we just stuff things into that one element array, and then we pull them out again, and then that is going to take care of the conversion for us. We don't need that at all. What we need to do is to use this awesome syntax for, and I believe I'm correct in saying that this is the arithmetic right shift. And that is something I get confused about because it is different between Verilog and JavaScript. But what this actually is doing is taking V and doing an arithmetic right shift on it by 0 bits. But in the process, that actually converts it into a uint32 representation. But it would have the sign bit, it would actually shift the sign bit down as well. So it's actually super useful. That allows us to do this conversion. And you can imagine, right, that we can do the kind of opposite operation, not really the opposite, but like sort of related operation here to undo something. And that would be to do this be a logical right shift? A logical right shift instead, which will do a bit shift pattern of 0 bits, but we'll actually cast it to an int32. That's so useful, and the beautiful thing that Ben also mentioned about this is that this is a super highly optimized operation in most JavaScript engines because of things like ASM.js. So that's great. That just means that this is going to be a really fast operation. We don't have any branching in this anymore, which is already going to be a performance increase. I mean, we're not going for performance here, but if we can get it, it's nice, right? That's great. So the other place where I do this is actually in the register32 class, and this is actually the other order of business, is that I went in and I just did this chore work of changing all of these places that we had like something and something next. This pattern that we have for latching values and making sure that the different pipeline stages aren't seeing the values of registers before they should. That pattern, we've actually encompassed that pattern in the register32 class that we made, and I've done a little bit of work here as well just to clean it up. I've made an enum with these indexes, and I'm still using the uint32 method here because I think it's just useful since we're keeping track of two values. I think it's just a useful way of doing it, and if it really becomes a performance problem, then we can actually change that later. But for now, I've just done this, and I realize now saying this that we might not see that much of utility out of the other thing we're doing. But if we get it, we get it. So what I've actually done is I've gone into all these pipeline stages, and I've just made everything a register. Even if it's actually not a 32-bit value, like funct3 is not a 32-bit value, it's a 3-bit value. That's kind of the point. I've just wrapped it all up in this for now. Shouldn't do us any harm. I guess there's some places where that could bite us, obviously, but I think if we're aware of it, it should be fine. And that just really helps in there are some instruction stages that are going to end up with tons and tons of we're going to end up generating a lot of information that we want to pass on, and this is just going to allow us to kind of get rid of some of the boilerplate. So that's it. Those two orders of business, consider those checked. Let's move on to store instructions. So one thing we're doing in the execute stage is we are calculating these three values, right? We calculate an immediate 32 value. We do that by taking the 12-bit immediate and sign extending it. That's what we're doing. We shift it up by 20 bits, and then we shift it back down by 20 bits. I guess then that this is the arithmetic right shift. Yeah, must be. I should really check that. It would be useful. I am just going to Google that in the background. really fast. Arithmetic right shift. You can't see this, but okay, so right shift and then there's an unsigned right shift. That's how they're calling them in JavaScript. Fine. So this does the sort of signed shift. Yeah, so that's what we're doing. We're sign extending to the 32-bit immediate here, and well, the problem with this, right, is that as we've just seen in our in the specification here, like sometimes we have this instruction format, and that's great. That's great for the ALU. But actually, we also have these other instruction formats, and we have other immediate values. And you can see here, you know, we have to pull a certain kind of immediate value here. The B-type instruction has an even more complex one that we won't go into for now. And then you can see it sort of gets progressively, you know, more and more interesting, the values that we build up here. So yeah, obviously it doesn't really make sense to actually calculate this value in the execute stage. It actually makes sense to calculate this in the decode stage. And what we're going to do is we're going to take all of those different immediate values and we're going to quote-unquote multiplex them into one immediate 32 value. And basically, that's a fancy way of saying we're going to take all those different formats, and depending on the instruction that we're dealing with, and here you can see we know which kind of instruction we're dealing with because we have these, you know, is this a register op? Is this an, I guess that's the wrong one. This one, is this an ALU operation? We're going to have these for all the different kinds of instruction types. So if we're going to have a store instruction, or if we're going to have a load instruction or a branch instruction, we're going to have a value for that. And all of this is going to move into the decode stage. So that's one of the first things to do. Let's just do that. So I'm going to take this, and I'm going to move it to decode. So that means, let's just put this here. It's not really organized, but we'll just do it for now. So we're going to need a register for that. A private is ALU op new register 32, and we're just, you know, in this case, like we're doing like a 1-bit representation, so we're throwing away 31 bits here. This either is or isn't an ALU operation, and likewise, we're going to be checking if something is a store, because those are the instructions we're going to deal with. So I also wrote this function bool to int, so that's just doing literally a conversion from Boolean to integer. Here we have our opcode. We need to get we constantly need to pull out like the next value or the value here, and like internally we want to deal with the next value, and everything else is referencing the value, right? Everything that sees the other side of this interface. So that's how we can check if something is an ALU operation. And if something is a store, well, let's just go to our thing here. For stores, they have this opcode. So let's just copy that. And then we can go back to the code. And we're basically saying, is the opcode, we just need to do a straight equality comparison here. Oh Lord. All right. Yeah. So now we're keeping track of if something's an ALU or if something's a store. None of these will ever be true at the same time, so that is not a big problem for us. We need to latch that value. I'm going to just separate everything I'm doing in this episode so it's clear to see. Is ALU operation, it's just this. Is ALU operation the value? And is store. Right, that's good. So now that means that we're going to have both of these values here. And of course we're going to want to get our immediate 32 as well, so let's do that already. And of course we're going to want to say that like immediate 32 is going to be a register, so let's just put that up here. intermediate 32 register. So how are we going to calculate this? Well, this is how we calculate the idea of this register, and that will be this, and it won't be value. It's going to be next value. So and we never actually need to twos anything anymore because of the fact that we're writing into registers. That's kind of useful. And if we really want to get a negative number, we need to just like convert it to a negative on like the interface that we expose to the outside world. Okay, so we could do this, but this is actually only the case when we have an AOU operation. If we have a store, right, we would actually need to break up the instruction a bit. We would need to get these bits and these bits, put them together, sign, extend them. So in order to do that, we don't really actually need to expose any of these immediate values anymore. So let's first, before doing anything else, let's just calculate our immediate, it's going to call it the store immediate, right? So the store immediate is, well, we're going to take the instruction, and the easier way to see this is actually just go to the load store thing itself, because it breaks this down really nicely for us. It gives us bit numbers. So here we have the like 31 down to 25. That's our first part of our offset, as it's called. So let's do that. We would take the instruction dot next value, and we could also just do this every time, but it's not really worth it. We're going to take that instruction, and we can just shift that down, and let's use this operation instead, right? Because this is going to allow us to like not do any sign extend, like not bring the what am I trying to say here? We don't care about it. Doesn't actually matter actually in this case. So we need to shift this down, and the way we're doing this, right, is you can see like to get the RD value here, we were shifting down by we were shifting down by like the first position of the RD. So in order to get the like this upper part, what we actually want to do is shift this down by 25, and then we're going to shift it back up. It's not the most efficient way of doing it, but it will get us what we want. Now, let me just stupidly count this out on my fingers, because I don't want to make a mistake here. So 31, 30, 29, 28, 27, 26, 25. So we've got 7 bits here. 7 bits here, and then we have 5 bits there. Oh yeah, that is actually 12 bits, of course. Really, really bad at mental math. So then what we want to do is actually shift this up by 5 bits, right? Because then we can bring in those other 5 bits. So that's like this part of the immediate. Just imagine, like, if this doesn't make sense to you, by the way, if you're thinking like, what is going on with this? Just write down like a binary number on a piece of paper, and then kind of like label the number positions, and then just go through the motions of like writing down that number like shifted over by a certain amount. Remember to make sure that you're going to cut off the zeros as they move past. So if you take a 32-bit number and you shift it down by 1, you lose that 1 bit, so that you ignore that, and then you're keeping everything to the left. So by doing this, we're shifting down these 25 bits. We should actually mask this off as well. We don't, like, strictly speaking, we can get away with not doing some of this stuff, right? It's not necessarily needed, but just so I don't make any mistakes. Yeah, just go through that process. Sorry, picking up that other thread. Go through that process and just do these shifts, and you kind of see that we end up isolating these bits, and then we're going to stick them together. It's actually not as complicated as it seems, but if you see it just written down like this, it can be really confusing. So 7 bits, as we know, that is represented by, well, you can actually work this out, right? But we know it's 7f. So we can AND that with OX7f. That gives us 7 bits. Then we're going to OR this number. So we're going to we've shifted that up. There are a bunch of 0 positions. There are 5 0 positions here. Then we're just going to add in our other 5 bits. So in order to get those, basically, let's just copy that inner value there. And I didn't copy it. So in order to get those, switch back to the spec. We'll shift these down by 7. So shift them down by 7. And then we only want to get 5 bits. That's 1f. And then we don't need to do any more shifting. So long-winded, but that gives us our immediate value for store instructions. It's going to get way more complicated when we do this for other ones. Great. Let's actually just double check this, right? Just for sanity's sake. Let's say we've got an instruction, and so what we're saying is that the first 7 bits, 1, 2, 3, 4, 5, 6, 7, they're going to be all 1s. And then going down, what do we have between here? So then there's 5 bits there, 10 bits, 13 bits. So the next 13 bits are just stuff we don't care about that we're going to end up ignoring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then we're going to have another 5 bits, 1, 2, 3, 4, 5 of stuff we care about. And then there are another 7 bits that we don't care about. 1, 2, 3, 4, 5, 6, 7. All right. And then let's just do this operation and see what we come out with. So that is just I. That's just I. And that looks about right to me already, because we get 4k, which is 12 bits, but let's just satisfy. Yeah, that gives us 12 bits, and they're all 1s, right? So, excellent. That allows us to isolate the instruction. Great. And then we would call the other one, right? This is going to be the ALU immediate. That's what I'll call it. And we know we can get that by doing that. So how do we actually assign into this actual immediate 32? Well, let's just basically do some if statements, because that's basically what a multiplexer is. It's a kind of hardware set of if statements, more or less. It's a combinational circuit. You can Google that. All right, so if it's a store, and it's if this is store dot next value. So if this is a store, then this dot immediate 32 dot value is going to equal store immediate. And yeah, that's going to take care of any two's complement stuff for us. And then else if this dot is an ALU operation dot next value, then this dot immediate 32 dot value equals ALU immediate. And for now, we'll throw an error if we we'll just say not implemented, which will help us catch bugs if we have to introduce them. Okay, so now we've got our immediate value. We can actually go back to this point and we are
decoding immediate 32, so we're going to get that just out of decoded, and I'm just going to, for now, just do that like this. We're going to need to pass that on, actually, I think. We're going to need to pass quite a lot of this on, so let's pass is store operation, and let's pass immediate 32. So we're going to take these things and we're going to end up passing them on. And in decode, we didn't pass them on. This is fairly easy to catch, at least. Alright, so stuff we're going to take out of decoded. We are going to take out immediate 32. We're going to take out is ALU operation. Do we end up looking at it with... Do we end up even doing anything with that here? Is ALU operation. We only expose it, so we don't need that. We can just do this, and then stuff we're passing on, like we're passing on RD right now, we'll just say is ALU operation.value equals decoded dot is ALU operation. Yeah, and then we don't need to get the value because we're not passing a register there, we're passing an actual JavaScript value. So apparently, it's store operation, which it's not. And yeah, we'll just do this now, like passing on our own immediate 32. Okay, yeah, I kind of just did this because we already had this written in a bunch of places referencing that immediate. Great, so at this point, everything should just be the same, but now we have some information, right? So if we go back to the to-do, we've ended up taking this immediate 32 value, moved it out of execute, moved it into decode. And we kind of need to do some better opcode decoding, knowing whether this is a store or an ALU or whatever. Well, that we've already done as well, right? So now we know if something is a store, we know if it's an ALU. We've used S-type encoding, so we are getting everything out of that now. So now we get into more of the details of the store operation itself, which we're going to be implementing in the memory access stage of the pipeline. Funct3 is going to encode our data width. So we actually want to make sure that we pass funct3 along. So we're going to need to make another register here, funct3. We'll do the same thing again. And right down here, well, ALU operation is store immediate 32 funct3, and then store woof immediate 32 and funct3, and we're going to need a few other things. We're actually let's just take a quick look at the stores. So actually, this is some useful context at this point, beyond just decoding stuff. So you can see that we end up making use of RS2, RS1, and funct3. So RS2, in this instruction, RS2 represents something called the source. So they're both source registers, right? RS1 and RS2, but in this case, it's actually the source. That's the number we're going to put into the register. RS1 is something called the base. So RS1, the value of RS1 is going to be added together with our sign extended immediate, which is going to allow us to move the value 2k either side of whatever the RS1 value is, because remember, the immediate offset is 12 bits, but it's sign extended, so it can be a positive or a negative number, and we're going to add that to RS1, and that's going to give us a final address that we will store this value at. So that's how we work that out. And knowing that, we know that we need to actually make sure that because we're in the execute stage now, and the following stage to the execute is memory access, and you can see we don't have access to like RS1 or RS2 here. We do have access to RD, the destination register, and that's the destination register address, right? That's not the RS1 value. You see we have RS1 and RS2 in the decoded, but we don't have it exported to the next stage, so to speak. So let's just close that switch up because it's huge. So 2 more registers while we're here. RS1, RS2. Easy to forward those on. RS2. Did I not call it RS2? I didn't. Latching. RS2. Or I guess let's do them in order. RS2. And then RS1. RS2. Great. So now we have those ready to move to the next stage. Yeah, there's a bunch of stuff here in the spec. These couple of paragraphs, and I do advise, like, if you're following along with this, especially if you're like implementing your own in another language or also in TypeScript or doing whatever you're doing, which might be interesting in this way, I do advise like reading this document. This document is actually fairly readable. I actually, over the course of some days, I just put this like on a PDF reader on a tablet, and I just read through it, basically cover to cover, which is surprisingly like not a bad read as long as you don't mind reading like super technical stuff. It's written in a fairly understandable way. The information is very dense, but yeah. So if you're doing this, if you're following along, just read the information. It will give loads of context, and probably I'm not going to be able to give all the context as I'm programming away. There's a bunch of stuff in these next couple of paragraphs about alignedness, and we've spoken about that at some length. And I still don't have a complete plan for how I'm going to handle alignedness. I think I might actually make hardware for it, so I might actually detect unaligned reads and writes, and like kind of do the multiple read and write that will need to happen because of that in hardware. So I'll basically stall everything. Which is slow. I mean, it's just slow to use unaligned accesses, but I think this is going to be the better way, maybe even the simpler way, because the other option that we have in this is that you can take the, and this paragraph actually describes it a little bit. It mentions that what you can do is you can bump this up to like an interrupt handling kind of thing. You basically trap whenever someone is doing a misaligned access, like hardware, and you go and run some code that you expect to be there as a kind of interrupt handler, and you kind of force the software to realign, to do realigned loads and stores, and figure out a value, and then sort of basically give it back to the processor. So yeah, that's a possibility, but I have the feeling that might bring its own complications. So I'm thinking of doing hardware. I'm not sure yet. I just thought I'd mention it now. We're probably going to see how it can get a bit complicated, because, well, that's the next thing. Let's actually get to writing these stores, because now we have all the information, right? Let's see how we can implement stores. Just want to check where I am, like on time. All right, it's pretty good pace so far. So let's have a look at the memory access stage, right? So here we are. We don't really have anything. This is just like, placeholder stuff. So by the time we get to the memory access stage, we're getting these execution values in, and these are these values, right? So they're the ALU result. This is like we might be writing that ALU. If this is a store. We don't ever write the ALU result. The ALU result, that's one of the nice things actually about this whole thing, is that if you have
an arithmetic instruction, then you're not also going to be doing a store. It's kind of the basis of the architecture. And yeah, the reason maybe I shouldn't even get into this, but the reason that like other architectures, like non-RISC architectures, do allow you to do things like do an arithmetic instruction and then store the value to memory. And they'll offer even more complicated things like do an arithmetic instruction, then store the value at memory based on some crazy offset system that you can calculate or encode in the instruction. And of course you think, yeah, that's in one instruction, so that's fast. But the problem is that can actually take multiple instruction cycles, or it can force the processor, because it's so complicated, to actually run at a slower speed. And the idea with RISC processors is that they can actually do these really atomic small operations, and you can just pack loads more instructions. Like you can execute them ideally in like a one cycle case, and then you just pack more of them together. And in the best case, you just run the processor faster, and that can be a good thing. That's just side note. It's not really important for now. So we're getting all this stuff in, right? So we're getting the immediate value, and we are getting the fact that this is or isn't a store. So I mean, at this point, we can just do our if statement. If and let's get if this is a store out, and let's get the immediate 32, and let's get rs1 and rs2 out. We're going to need those things. If this is a store, and we're also going to, we might not actually need to assign all of these to the next register, because this is going to be the write back stage, and we're only going to write back if we've got something to do. Like if it was a load, we might need to write back. If it was a AOU operation, then we'll need to write back. Anyway, we'll get to that later. If this is a store, then we need to work out what we're going to store, basically. And we need to figure out an adjusted address. So the address that we're going to store at is going to be the immediate 32 plus RS, and I forget, so I'm going to go back to the spec. Is it RS1 or is it RS2? So the base is RS1. Okay, so we're going to add RS1. And let's put this whole thing in a twos, right? Because right now we're not in the register domain, as it were. So we want to perform that operation. And notice that like the immediate 32 here would actually be a positive number either way. And we're basically relying on the fact that as we overflow this, that will give us the same operation. Like the fact that it's a negative number and it's encoded in 2's complement, and we add it, will still actually give like the right result as long as we put it back into 2's complement representation afterwards. Okay, so that's our address. Our value obviously is RS2, and now we're going to do a store, and we just basically need to see which kind of store we're going to do. So let's make an enum, and we can export it as well. I don't know if we're going to use it anywhere else, but this is going to be the memory access width, I guess, because it'll be the same for loads and stores. So the way we're going to have three values here, right? Not three values. This comes out of funct3. This is the encoding. Let's just flip back over to the coding. And we can see funct3 here encodes the width, and the place where we can see the actual values is on 104. So if it's 0, then it's going to be a byte. If it's 1, then it's going to be a half word, and if it's 2, then it's going to be if it's 3, then it's going to be a store word. And you can see actually for the loads, those should be the same. So we can just bundle those together into a memory access. So what did I say? If we had 0, then we considered that to be, I guess do the name on the left, obviously. So this is when we have a byte. When we have a half word, then we're dealing with 001. Let's just align everything. And when we're dealing with a word, Cool. Okay. Yeah, I haven't looked into the 64-bit instruction set, but I'm curious. I'm guessing that when it's a 64-bit value that you would store, so a double word in this case, I'm guessing that it would be this is 2, of course, yeah. So we've got 0, 1, 2, but I'm guessing we're going to skip 3, and we would go to 4 straight away. So we would end up having just a one-hot encoding kind of thing. But I don't actually know if that is the case or not. I guess there are some proposals or extensions. I don't know if they're all the way through for larger sized, like 128-bit kind of instruction set architectures, and they would have to do something different, right? Because you still only have 3 bits in that case. I actually don't know. Okay, so now depending on that, right? So let's just do a switch here, and we're going to say, and we need to bring funct3 here as well. So depending on funct3. This is fun. So if we have a memory access width of byte, then we're gonna be calling a particular kind of store thing on the memory, right? Because right now we actually don't have access to, we don't get the memory bus in here, and we kind of need that. So let's actually go and fix that straight away. So in index.ts, here we can we have our memory bus, that's our system interface, as many different names of things as possible. We'll pass that in as the bus, and it's saying, yeah, like that is not valid because that's not part of the thing, but it now is valid. So here, let's also keep a private representation of the bus, and we'll say that the this.bus equals params.bus. Excellent. And then kind of what we're going to want to do, right, is right now the bus has 2 methods, read and write. We're going to change that because like the instruction set is going to give us this ability to write bytes, half words, and words. And by the way, that also modifies how alignedness works. I should have mentioned that before. Obviously, if you write a half word, it can't be. It's not only 32-bit aligned anymore. I mean, that is something they could have done, but it's kind of useless in that case. So in order to accommodate for that, things have to be naturally aligned for their type. So 32-bit values need to be 32-bit aligned. They don't need to be, but it's better if they are. 16-bit values need to be 16-bit boundary aligned, and 8-bit values can obviously just read-write to bytes, right? They're just going into byte address. So we need a read byte / write byte. We need a read half word and a read. Then we could just call them read 8, read 16, 32. Maybe that's actually easier. Write 32. So what we actually need here is like write. Actually, maybe we'll just use this same. Maybe we'll actually just use this same enum instead of having a read 8 and a read 16. We'll just have a read, and we'll pass memory access with. So in this case, what we'll do is we're gonna do bus.write, and we're gonna say the address comes first, I believe, and the value is next. So that's rs2, and then we'll use the same memory access width to say that we're doing a byte aligned. So this is obviously wrong at the moment. We need to change the interface. Okay, yeah, let's do that. So if we were to go to the definition of this, I guess I pressed the wrong button there. I tried to debug. Still getting used to things here. system interface. We'll just go here, and we have this MMIO device interface. They're just going to take this memory access width, which we'll just call width here. We need to bring that in. So we're implementing this interface. It's kind of funny, right? Because we're saying, yeah, we implement the MMIO device interface, and yet our read method is not actually valid, right? Because this is the interface. This is one of the things I've had trouble with in TypeScript, is like classes that actually implement interfaces not having like correct implementations, but TypeScript still being okay with it. Yeah, it's kind of a strange thing. And also, someone mentioned to me in the comments of the last video, like, hey, you actually you described this interface, so you don't need to give the type of address here, but you actually do, because if you don't have the type, then it just doesn't know. Kind of weird, but it's just one of those things. So the width is also, well, it's a number, but let's call it a memory access width. Someone else also mentioned to me that maybe we should use opaque types, which is actually something that is really useful. I'm probably not going to do it now, but I might do that in between. I might do some behind the scenes for that. Opaque types, if you don't know what they are, you should Google it. It's a TypeScript thing, which basically what it allows you to do is take something that is like a number type, but like sort of wrap it up in a kind of zero cost way, at least a zero runtime cost. There's some compilation time cost. In a type safe way, so that you actually have to explicitly say that something is an address. And what that saves you from doing is, if you have like a write method here, you can see both parameters are actually numbers. So you could easily, and I do, get things like, which order do I write? Do I write the address or the value first? You could save that by forcing the user to say, here's my number, but it is also an address. You can't just sort of do it in an implied way. That's pretty cool. It's not something we're going to do now. It's a nice TypeScript trick, so we'll take a look at that at some point. I believe that was Zauber who mentioned that. Okay, so we've got our width, and we're going to need to do away with this align in this thing now, because the align in this thing is not going to be correct if like we're doing an 8, like we could leave it in there depending on if we're doing like a 32-bit value or an 8-bit value or whatever. But we can't just like zip these 2 bits off the end and say, yeah, everything needs to be aligned. So we'll get rid of that for now. Just comment it out. So we're just going to pass these values along, right? We can't. This is what I'm talking about. We can't just nibble these bytes off. That's not gonna fly. We're going to have to deal with it inside the devices themselves. So for a read, let's just go in and solve the problem, because this is going to get a bit hairy. If we thought trying to pull that immediate instruction part apart was a bit hairy, then this is really gonna do it. So let's go into ROM. Start with ROM, because ROMs only have reads. And you can see that we actually have a ROM. We're dealing with a uint32 array, so we don't have bytes here. We just have this big 32-bit chunk, and that's kind of, I think that's going to be relatively accurate to how we really deal with memory in the hardware. So I'm going to leave it like this. I'm not going to like take the shortcut and byte align it. I'm also not going to take the shortcut and just like reinterpret this array as a uint8 and use that methodology to write, because I think we can learn more by doing it like the tricky way. So again, we're going to need to do this. We're going to need the width, and the width is going to be a memory access width, which means that we're now going to be doing this wrong because we don't pass the width. We just need to pass the width along. Same thing here. that's actually going to be wrong because it thinks we don't need it yet. Where are we in ROM? Okay, so we get the width now, and like, okay, so this calculation, right? This calculation would be correct if we were dealing with a 32-bit number, and also if we didn't have the last 2 bits of the address. So let's make a switch statement in here. Switch. We're still assuming everything is aligned to the natural width, right? But not to the... yeah, it's going to get confusing, so just strap in for a minute. Okay, so when we're reading a byte, we get that width in, and we now need to see which byte do we read, because we need to, like, we can find an address, right? The address that we're gonna be looking into is actually our address, where we nibble two bits off the end. And yeah, I'm going to do it like this because yeah, I want to avoid that we accidentally sign extend this, right? Or is this the sign extended way? No, right? Oh, I'm driving myself crazy here. This is really confusing me. So 1, 2, 3, 4. So that keeps it in. If we do this, if we were to shift it down by 1, we would actually move that bit 1 down. So I think this is what we need to do, right? I could also just do the this is nibbling those 2 bits off the end. So if we made that a 3, right? And then we nibble the 2 bits off the end, and then that's fun. Yeah, so I think that's all good. I don't know if any of what I just did made sense there, but this is the address that we're going to look into this 32-bit array with. So we would use this here. Okay, but we've got a byte, right? And now that means that there are 4 possible places that we could be reading from this 32-bit array. So, and the way we actually get those is that just by looking at the last 2 bits. So I'm going to call this the offset. I don't know if that's a great name for it. We take the address and we're just going to take those 2 bits off the end. And now we're going to like do different things depending on what the value of those is. So should I do a nested switch statement here? Is that like too nasty? Just sue me if you think it is. So in the 0-0 case, let's do this all like this. By the way, the spec mentions this, of course, and the spec says that where does it say? We get the address. So the effective address should be on the boundary. Naturally aligned. Where does it mention this? Copy from. There's a 16-bit sign extends it for. Yes, this is what I'm looking for. The SW, SH, and SB instructions are 32-bit, 16-bit, and 8-bit values from the low bits of the register. So what that means is that if we were to say, give me, like, I want to store, like, in the case, okay, so I think, I'm actually confusing myself with this one, because that's stores anyway. On loads, if we were to be loading the byte at 0, we would actually be loading the most significant byte. So we're going to be, basically, we take
this gives us the value. We can actually just get the value up here, right? That's not going to change. We're always going to need that value. Not what I meant to do. I think I pressed Command. So this is our value. What we actually want to do here is want to get the value, and you can imagine, right, that in hexadecimal terms, that like it's that part that we're dealing with. So we're taking that part of the value, and then we're going to shift it down by 24 bits, which should put it just like in the 8-bit position. Should put it down here. I hope that makes some sense. I'm going to return that. So in the case that we're trying to get the first bit, then you can imagine that what we're trying to do actually is try to get this, right? We're trying to isolate that byte, and then instead of shifting down by 24 bits, we can take 8 bits off that, right? Because we're not like this far up, we're here, so we just shift that down by 16 bits. Again, if we're in this position, then that means we're down here, and we only need to go down by 8 bits. And in the end, when we're at 1, 1, we don't need to do any of this stuff. Like I could just do like this and say shift down by 0, but we could effectively just return like this statement, which is a little bit nicer, I think. Okay, that is our read correctly implemented for the 8-bit case. It gets, I guess, slightly simpler for the half word 16-bit case, because the offset is no longer actually 2 bits, but rather just 1 bit, right? We're either getting the top 16 bits or the bottom 16 bits. So that kind of makes life easier, right? So we actually just need that 1 bit. We don't really even need to do this as a switch statement, but I will, just for the consistency's sake. We certainly don't need all 4 of these. So in this case, right, of course, what we actually want to do is, like, we want to isolate this part, and we want to shift it down by 16 bits. And in this case, it's just like that. Great, that's it. And in the last case, the word case, it's the easiest one because we just have the value. Great. Maybe not as complicated as it seems. We can basically copy this exact method to RAM because nothing really changes there. Yep, so let's copy the entire method, why not? Go over to RAM and replace this with this. Then we're going to need to bring that in. We don't have RAMs, we have RAM size, and we have RAM. Everything else, all good. And we don't have a write, of course. We don't have write functionality in ROM. We do have write functionality in RAM. And then we are also going to be taking this width parameter. So this is going to be the same thing now. We're assuming that we've been given either a 32-bit, a 16-bit, or an 8-bit value, and we need to write it into one of those positions. So we can even now take all this as our starting point, because it's going to be this, but slightly more complicated. So we can't call this value, let's call that current value, because we have a value coming in. So now what we're going to be doing is we're going to be looking into our offset, not to like
set the place that we're like taking from the value, but we're actually going to set the place that we're writing into the value, like writing a new value. So all of our returns here, well, we're not going to be returning. This method returns void. How do I get to the end? It's getting hairy. All right, good enough. So the tricky thing we're going to do here, right? We're doing more bit manipulation. We need to write this, like our value, into this position of the current value, which means we need to take everything from the current value, like except these, and let's just do it in the dumbest possible way, right? So no, it's not the dumbest possible way, of course, because there are dumber ways of doing it. But what we're saying is we don't want those bits, but we do want those bits. So we take the current value, and then we're going to OR in our actual value. But of course, our actual value is not in the right place anymore, right? Because it's our actual value is going to be down here. So we actually need to shift it up by 24 bits. So let's shift that up by 24 bits. And then what we're doing is saying this.ram, this address now equals this. And we might need to do some fancy stuff here, because this is the address we're actually supposed to be using. So that's it's not really the address, right? This is sort of the address, but this is the true address. Oh, that's so jank. I'm actually going to make a variable called true address, which is let's call it masked address. That sounds like less jank. It sounds more like we know what we're doing. So we take the masked address and we'll use that here, and then that also means that now we can write into the masked address. Number, it has no call signatures. What's going on here? Why does it think we're trying to call number? That was weird. Oh, okay, because I didn't have that semicolon. This is just one of the places that really reveals why you should use semicolons and why they're not optional in JavaScript and TypeScript. People say, oh yeah, it's okay, the machine will do automatic semicolon injection for you, and this is a case where that goes wrong, right? Because what it's trying to do is saying, oh, there's some white space, what's this down here? And it's saying that basically this should be a function and these are the arguments. So obviously we don't want that. I mean, we're not keeping this line. That sort of doesn't matter. Just a lesson, use semicolons. They don't hurt. You're not saving any space by not using them or something. I guess you are, but if you're gzipping your code as you send it down the wire to people, then it just makes no difference, right? You're compressing it so heavily. There's so many instances of semicolons in your code that you're going to compress it out anyway. Yeah, that's my little rant. So that's the 0 case. Let's have a little think about the next case, the 1 case. So then, of course, right, we want to ignore those bits, and we want to take our value and shift it up by 16. And that's that. You can see where we're going to go for the next one. Not 3. We're shifting up by 8. And then in this last case, the only thing we don't want is that, and we don't need to shift the value because it's already in 8 bits, in the right position rather. Okay, so that's our 8-bit case. Could see a little bit more complicated, but not that much. Yeah, let's copy the switch. Why not? like this. Get rid of those first two. Get rid of the first bit. And now what we're doing is saying that we are... So we're writing into the top... Writing into the top 16 bits here and keeping the bottom. And here obviously the opposite. Keeping the top and writing in those. And in the word case, we are saying it's even easier. So we are just writing the value. This is already 32 bits, as far as we know. That's it. We haven't dealt with alignedness. This is, you can see why alignedness might get a bit complicated. I mean, obviously in hardware, this actually does get a bit easier because right now we have to take a value, we have to mask it and stuff. But the beautiful thing about the hardware, especially if I end up, from what I know of the RAM chip that is on this board, and this is the first video of this kind where I actually know the board that I'm probably going to use, which is this one, the RTA7. Sorry if the focus didn't work there. That board has an onboard RAM chip, and the interface, I haven't fully researched this yet, but the interface between the FPGA and the RAM chip, which hopefully I can get from Xilinx themselves, is probably just going to include some ability, even though the natural size of this thing is going to probably be it might not even be 32 bits. I think I read on the datasheet that this is a 16-bit wide RAM. It sort of doesn't matter. You can there's going to be one hardware abstraction layer above that, which will be exposed probably on some other kind of bus format, like an Avalon bus or a Wishbone bus. I'm not going to get into those now. They're probably going to expose some sort of functionality to just read and write bytes or half words or words anyway. So some of this is going to go away with that. But yeah, it's a little bit more complicated here, but this is actually nice because it sort of shows us what the values are really doing. Have a quick peek at timing. What's that? 1 hour and 7 minutes. That's actually lightning fast pace for the videos that I've been making so far. Great, so we've actually written these interfaces out properly now. So we've got our, that's our read interface, and we got rid of this alignment stuff because we're dealing with that there in place. To fix the interface here, get rid of our alignment stuff, get rid of the shift that's happening. Seeing as we are... What doesn't it like here? Expected 3 arguments, we've got 2. True, absolutely. Finally. Finally things know what the interface should be, but only because the RAM has actually defined that. So, great. I think, hopefully, we've gotten that to a point where that should work now. So, okay, so we're in instruction. What does the instruction fetch look like here? Oh yeah, we do a read here, of course. So we actually need to fix that. Memory access width dot word. Yeah, we want to pull 32-bit words out when we get instructions. Close, close, close. Hopefully all of those are good. Memory access. So, in the case that we are trying to store a byte, well, let's actually make sure that we only take 1 byte off this, so let's just do that. We're storing a byte and we're saying it's a byte. That should be enough in this case. We'll just break from the switch after that because I don't know if we can return yet. Probably need to do some other things. If we have a half word, just 16 bits, half word, and if we have a word could also just like write funct3 here, but this is nice and explicit. We can just write the full rs2 value. Yeah, okay, so that's it. That's storing. We've stored a value at this point. And this address, by the way, you can see that we're doing an addition here. This is one, like, I'm not gonna do this now. I'm gonna write a to-do. This should be done in the ALU. Because, yeah, we're doing an addition there. There's no reason for us to be, like, doing an addition at this stage of the pipeline. And this, I'm just going to touch super briefly on this. It's more something that I want to talk about when we do the actual hardware. But one of the reasons that you split stuff up into pipeline stages at all is because if you don't do that, then you can end up with chains of digital logic which are very, very long. What does that mean? Well, even now we're just dealing with the idea of registers and that kind of stuff. And we're doing operations like ANDing and ORing, and we're even doing high-level stuff like adding and subtracting and stuff like that. But as you well know, all of those things are actually just logic gates, fundamentally, right? Adding stuff together is just taking loads of bits in and running them through loads of logic gates, and sort of they run through all the logic gates, and on the other side you get a bunch of other bits and they represent your addition. Same thing with a multiplexer, which I mentioned earlier, like this if statement. It's a set of logic gates actually that just sort of take your values, crunch them in some logic-y way, and put something out on the other side. Now, if you have just like, imagine all the things we're doing in this processor, what you end up with is just a really big chain of logic gates. And the reason that what we're actually doing here with a pipeline and also with this concept of registers is we're making it so that we have checkpoints in between, right? We can take those huge long chains of logic and we kind of put checkpoints in the middle of them. And then we break what are really long logic chains into more manageable logic chains. And why is that important? The reason that's important is because in the real world, in all situations, right? But it definitely doesn't come up in our software. In the real world, there's something called propagation delay, right? And other things, right? The propagation delay is really the simplest possible part of this whole thing. There are more timing stuff that we will talk about when we talk about the FPGA. But imagine just propagation delay. It actually just takes time for values to move through these logic gates. So it's not like when you put something on the input, it's instantaneously available on the output. It takes time. And even when it is available, it kind of takes time to stabilize as well. So there's time just to move the kind of electrons through the transistor, as it were, right? Won't get into transistor stuff now, but electrons. That's all it is. It's big electron soup, charges, differences, and all that kind of stuff. Like it takes time for that to happen. And then it kind of also takes time for things to settle out. So then things settle out. So all of that takes time. And the longer your chain is, you kind of accumulate that huge amount of time over time. Now, obviously, you don't do everything in serial in hardware. You're doing as much as possible in parallel. So you're computing all these different values. They're just going through their own circuits. But things will always take the length of time. Like in your set of parallel operations, you're always going to have one longest path in that. So, you just want what you really want to do is you want to design for short paths, because otherwise you can't get what you need to get done in one clock cycle done in time. That's really the crux of the problem, is that if you get to a certain point, the clock cycles are so short, like they're so unimaginably short lengths of time. We're going to be building a really slow processor here, and we're going to bump into these things. Like unlike the gigahertz processors, this is like, it's like magic basically. At some point, obviously you don't on an FPGA it's different because it's way slower than an actual silicon chip. All that said, the time of your clock cycle is going to be like the limiting factor to how much stuff you can do. So we need to minimize the amount of stuff we can do. Okay, that tangent, to reduce that down to its like actual value, we're now doing a random addition here in the memory access stage, which means we've now made the memory access stage as long as an addition would be, and kind of nothing else in here probably will be that long. So what we're better off doing is just moving this to the ALU stage, where we're already going to have paths that are at least as long as addition. And we're going to need to do the addition anyway, so why not stick it there where we know that that's already a constraint that we have to deal with. Yeah, that's pretty much it. That's why we should do that in the ALU stage and move it to this stage instead. Hope some of that made sense. For now, we'll just compute the address here because it's easier. Okay, I actually have the feeling that we might be at the point where we could just test this out with an instruction. Okay, I'm actually back here. It's the next day. And I've set up a kind of test harness here for checking to see if the stores are working as they should be. And I have already had a little play with this code, so I kind of know some things work already. But I want to take you through the setup I've put together, and also show you the one problem that I found while I was writing this, and have since fixed. And it was a very minor problem, but yeah, it's worth pointing out because perhaps some of you even spotted it while I wrongly implemented it. So let's just take a look actually. So in the first case, we know from the spec that we have these various forms of instructions, and that in all the store instructions we need two registers, one for the base address and another for the source that we're going to be using. So here I've set up a base address register that points to the beginning of RAM as defined by the memory map of this machine. It could be any other address for anything else, but so RAM is located here. And I've set up some register values here. So in register 2 we have dead beef, in register 3 we have code cafe, and in register 4 we have a bad idea. And these three instructions that I've set up, we have the immediate, and that's our 12-bit immediate, and at the moment I'm only using a very small value to offset this. In fact, you can see here that if this is the other side of the immediate, so that's all the most significant bits are all 0, and actually it's just 4 here. So what we're going to say is that whatever we end up writing into RAM here, we're actually writing it into address 2 with many zeros and then 4. And the register that we're writing here is dead beef, and it's a 32-bit. So when we execute this instruction, we would expect to find at address 20004 dead beef afterwards. Then on the next one, it's a store 16. And with the 16-bit stores, you don't store the whole register, of course, because it's 32 bits. You actually store 16 bits of it, and you store the bottom 16 bits. So we can expect that we're going to be writing this cafe value somewhere. The offset that I have here is 6, so this will be writing that 16-bit value here, and it's okay that this is not aligned on the 4-byte boundary because 16-bit values can be aligned on the 2-byte boundary, and that sort of actually is what's happening here. And so in terms of this register, if we think of this being at address 20000 blah 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 4, this is the first byte, this is the second byte, and then this would actually be offset 6. So this is offset 4, offset 5, offset 6. So what we're expecting after running this instruction is that we'd be writing into that thing, and if we read memory a 32-bit value with this, we would see dead cafe. That's the idea. And then for the 8-bit, it's all pretty much the same. We have a 5-byte offset, so again we'd be writing here, and we just write the bottom byte, and of course that's offset by 1. So if we again imagine that this is our memory value, this would be 4, and then this would be 5. So we're expecting to overwrite this part. So we'd have dead beef, dead cafe, and then sort of DE, EA cafe. That's what we're expecting in this case. And then I haven't tried it yet, but we can go through and actually make sure that this works with negative numbers as well, and that the sign extension works properly. We'll set up a little harness for that as well. Okay, I've put a little breakpoint here. That breakpoint executes when we run cycle, and only when we've run all of the pipeline stages and we're going back to the first stage of the pipeline. So basically when we've done one whole instruction. That's about all there is to it. So let's actually run it and see if it works correctly. So we hit this breakpoint, and the way we can test is to just read some values out of memory. So we're in the context of this RISC-V instance. By the way, just incidentally, I found out through reading the spec more closely that it's not RVI32, it's actually RV32I, which makes sense, but it kind of doesn't roll off the tongue as well. I mean, I'm just wrong, but yeah, maybe I made the mistake because it sounds better. I don't know. I'll fix that at some moment. But we're in the context of this instance, so we can say this, and we have access to the memory bus, and we can just read a value from it. The value we're going to read is 004, and we need to provide the data width, because we can read 8-bit, 16-bit, and 32-bit values, and the 32-bit value is just represented by this as per the spec. So executing that, I see that we actually get 0, which is incorrect, so maybe I didn't have the right number of bits here. 1, 2, 3, 4, 5, 6, 7. Yeah, okay, so I was missing a 0 in there. That's looking more reasonable. If you're a connoisseur of cool numbers, then you'll know already that that is dead beef in its decimal form. So good. That's the simple case. That's the simplest of all cases, right? Because we're just like taking the value, working out some offset, and we're just writing the register. So nothing strange can really happen in that case. Let's press play, having executed the second instruction, the store 16 here, and let's read from the same 32-bit value. Now, of course, you'll say, yeah, but we wrote into address 6. But yeah, that's still going to be, everything is still conceptually 32-bit aligned, or 4-byte aligned. So if we're reading from here, we're going to see that we've overwritten, this half of the memory value, which is exactly what we want to be able to do. So let's just check that. We see dead cafe, that's great. And then we execute the final one, the 8-bit, checking, and we see that EA has been replaced, or the EF has been replaced with EA. So excellent, that's really cool. Those are all working correctly, and actually we can also see, for instance, if I set this to 6 and I say instead read a 16-bit value, we can also do that. We could also read a 16-bit value going from 4, and we would just read the kind of dia part now, which is nice. We can do that even if we haven't written that. We can sort of interpret memory in 16-bit, of course. And reading 5 for an 8-bit value gives us that EA. Perfect. And of course we can do it for anything else, like DE. So that all works as should be. Let's take a little look at, let's actually set this value to 5, and then we will execute store 32, but we'll set its immediate offset to be -1 in 2's complement form. So in like a 12-bit number, that would be FFF, or where all of the bits are 1. So we'll just do that. That's the easiest way to test all of these kind of things. And inductively, we can assume it will work for all cases after that, right? All negative cases. So let's try this. Run. We get to this point. We can read our 32-bit value. And 0 is not correct. And I didn't mess the number of zeros up here again. Nope. Okay, so something is up, probably with how we are sign extending. In decode. Oh, this actually makes sense because we're not sign extending. Yeah, we isolated the 12 bits of the value, and we're not sign extending it. So here we're sign extending it, right? We take this 12-bit value, we shift it up by 20 bits, and then we shift it down again using that what is the actual arithmetic right shift. And I'm going to get that wrong so many times. I really apologize. Yeah, and we just need to do the same thing here. And actually, I'm looking at this, and I think if we end up doing the same thing, we're going to end up with this longer and longer expression. So I think let's write a utility function for it. So sign extend 32, and we'll say, well, yeah, of course. So like here we have a 12-bit number, and in order to work out these values, we need to shift by. We take 32 bits because that's like our target value, our target, bit width. And we would say 32 minus the number of bits in this value. So this is now a 12-bit value. So we do 32 minus 12 gives us 20. And that's the number we have to shift by. Yeah, okay. So we need to take in the number of bits, which is a number. And then we'll take in the value, which is also a number. And what we would do is we'll say value. And we're going to first shift it up by 32 minus bits, and then shift it down by 32 minus bits. And yeah, you could make a constant for this and everything, but I'm going to leave that up to the JIT to work that out for us. And otherwise, I just don't mind that much what happens. Got this right? Bits, value gets shifted. Okay. So we'll wrap that in sign extend 32. It's 12 bits. And we can also do this, right? Sign extend 32, 12 bits. And just get rid of that. If everything works, then these two things should be equivalent now. Let's just run the test again, because that's the quickest way. Yes, perfect. Okay. Great. So now we've got that. Now we've got that value, that sign extend, and I'm confident that that will also work for the AOU, because why wouldn't it? One of the things we have now is that we don't need this immediate value at all. Anything we do with immediates here, we're going to assume that like the outside world, like the interface to the next pipeline stages, is going to be the immediate 32 value, right? It's not going to matter to the rest of the machine where this immediate 32 comes from. But I'll just leave that for now, and I'll get rid of that in the next one. Yeah, so, well, if you made it this far, then I just want to say thanks. Thanks for watching. I guess you must be finding it interesting in some way. If you've seen anything that you think, oh, that's kind of weird, why did you do that? Or you've definitely done something stupid there, then just let me know in the comments. I'm open to learn, and I was really glad to receive a few nice comments on the first video, where I definitely learned something. So yeah, feel free to give any feedback you might have. I'll see you next time.